Welcome to Calculus. Today we will investigate finding derivatives of integrals using the fundamental theorem of calculus 2. We'll take a look at 4 examples. Our first example is d dx, so the derivative of the integration from 1 to x of the function square root of t squared plus 1 dt. Now I want to use the fundamental theorem of calculus 2 to take this derivative of the integral. So let's remember what the fundamental theorem of calculus 2 states. Essentially, that theorem says that if I've got a function f of x that's continuous on an open interval that contains the lower limit of integration, which in this case is 1, then I can assume that the area function is an antiderivative of the integrand f of x on that interval. So one way that we can state that real succinctly is the derivative of the integral from a to x of f of t dt is going to be f of x. And really, it's a statement about the fact that differentiation and integration are inverse operations. So I really have the same setup here with my first example as the statement of the fundamental theorem of calculus. So really all I have to notice that the integrand f of t dt, when I apply integration and then take the derivative of the integration, is going to result in simply f of x. And notice that x is the upper limit of integration. So I just need to find those parts here with this derivative of the integral in example 1. So my f of t is the square root of t squared plus 1. My upper limit of integration is x. And so it's a real straightforward application of the fundamental theorem of calculus 2. This has the value of the square root replacing t with x squared plus 1, and I can assume that's my f of x. Again, it's really an observation that the derivative and the integral are inverse operations. So that's a very straightforward application. Let's take a look at one more that is similar. So this is the derivative d dx of the integration from 1 to x of natural log of u du. Just like with our previous example, I'm going to locate the f of t. And again, just to kind of keep in view the fundamental theorem of calculus 2, if that function is continuous on an open interval containing 1, so definitely natural log of u is continuous in that open interval and 1 is in that open interval. Just considering the natural logarithm function. So that's its function. It would not be existing in the negative values, but definitely 1 is within that open interval of its continuity. The fundamental theorem of calculus 2 again states that the derivative of that integral from a, which is a number, to x, the variable of f of t dt, is going to be f of x. So we've satisfied the hypothesis of that theorem. We just need to apply it. So again, we had found that f of t was natural log of u. Upper limit of integration is x, so those match. So all I have to do is apply the theorem. My f of x here is going to be natural log of x. So those two examples were very straightforward applications of the fundamental theorem of calculus 2. Let's take a look at an example that does require us to use the chain rule as well. So here I've got the derivative d dx of the integration from 1 to 2x cubed. So initially I noticed that this upper limit of integration is really another function. So I got to deal with that, and that's why we have to use the chain rule here of the function square root of t squared plus 1 dt. Now, let's keep in view still our fundamental theorem of calculus 2. It states that the derivative according to x, of the integral from a to x of f of t dt is going to be f of x. But I need to take into account that this upper limit of integration that's given by the theorem is simply x. That's the identity function, whereas here I have the another cubic function, 2x cubed. So the way I want to approach that is really an application of the chain rule. So let's just kind of say how that might look. This whole thing is the f, capital F function. So I'm finding its derivative. Again, we're just considering that this, without that ddx, is going to be my capital F of x. In a way, it's the antiderivative. So I'm going to set this up using the idea of chain rule. So this is going to be equivalent to df, capital F, du times du dx. Now I want to use this because really I'm going to place this, make sure that I don't say this wrong. Let me adjust what I'm saying about f of x here. F of x is really the integrand. So I'll kind of narrow in my view there. Really, that's my f of x. So I'm going to separate these differentials. This is going to be d du times capital F of x times du dx. So notice I'm just treating these like factors. Now I can make a substitution. We identified f of x as my integrand. So this is going to be d du of the square root. In fact, I should have included that integration, I see. So back to the original. Okay. So let's get that, all the components here. So I'm going to call this the integration from 1 to 2x cubed of the square root of t squared plus 1 du dx. And again, that's just a substitution. The capital F of x is my integration of the function. It's the area function. Now what I need to do is I need to substitute in a simpler dummy variable for that function 2x cubed. And since I've got this set up with the u variable for the chain rule, I'm going to use variable u, and what I'll define u as u equals 2x cubed. Let's go ahead and find the derivative of u because we got to find that next. So du dx is going to be the derivative of 2x cubed, which is 3 times 2x to the power of 2, or 6x squared. So let's rewrite this derivative. So it's the derivative with respect to u. And now we're ready to substitute u for my upper limit of integration of t squared plus 1 under the square root. I forgot my dt here. Du dx. And at that point, we're ready to apply the fundamental theorem of calculus, because now you see that I've got this expression, d du of the integration from 1 to u of the square root of t squared plus 1 dt, really is set up exactly as I've got the fundamental theorem of calculus 2. So what I'll see next is that this is going to equal the square root. I'm going to substitute in that upper limit of integration for the t value, so square root of u squared plus 1. But then notice, according to the chain rule, I also have this factor du dx. Now I define that over here on the u substitution as the derivative of 2x cubed, so that's 6x squared. So I'm going to substitute du dx for its actual value. And then my last substitution is going to be to take u and substitute back in 2x cubed. And this will finalize this question. So now I've got the square root of 2x cubed substituted in for u squared plus 1 times 6x squared. And we can simplify that to say, we'll put that 6x squared first, so it's clearly outside the radical. And then we'll square 2x cubed, that's 4x to the 6th plus 1. And that completes it. So here we do have to apply not only fundamental theorem of calculus 2, but the chain rule as well. Our last example is this one where our limits of integration are switched. So notice this is the derivative ddx of the integration from variable x to constant 5. So notice that flips the order from what I normally see in fundamental theorem of calculus 2. The integrand here is sine of t squared and then dt. So the first thing I want to do, if I want to apply fundamental theorem of calculus 2, I've got to get those limits of integration in the right spots. We'll put this again, so it's ddx of the integration from constant a to variable x. That's the order I need, of f of t dt equals f of x. So before I can apply the theorem, I need to flip or reverse these limits of integration. And that's pretty straightforward to do. Remember, I really just changed the sign. So I can call this -1, that's flipping the sign. And notice I'm letting it pass outside the integration and the differentiation. So that's going to be -1 times ddx of the integration now from 5 to x. If I include the negative sign out front, I can switch the order of the limits of integration. Once I do that, it's set up to apply the fundamental theorem of calculus 2. So this is going to be equivalent to -1 times sine of x squared. And that can be reduced to negative sine of x squared, and that is complete. So with that one, again, very straightforward application of fundamental theorem of calculus 2, with the one change where I had to switch the limits of integration. Well, thank you for joining for this investigation of taking the derivative of an integral by applying the fundamental theorem of calculus 2. See you soon.